Okay, so in these videos that I'm calling In a Nutshell, I'm basically going to run through quite briefly, so it's not going to have every single bit of information you need, but it's going to be a good revision tool. So basically go through each unit and give you the gist of what you need to know. So we're looking at the first one, which is Unit 1.1, which is System Architecture. So I'll go on to the next slide. Right, so first bit, the purpose of the CPU. In case you don't get that question, very unlikely it would just ask you straight off the bat, but basically the purpose of a CPU is to process data. Normally they use this input, process, output model. So essentially the whole idea is that continuously the computer is looking at some sort of input, doing some sort of process and giving some sort of information back out. Whether it's checking emails, playing games or doing whatever, it is essentially processing data as it does that. Right. It does that using the fetch, decode, execute cycle, or the fetch execute cycle. So I did show a video to the class the other day, but I'm going to put it on a link above this on the website so you can look at a person showing it live because it's a lot easier to see. But these are the steps, okay? So all you've got to understand is that the CPU is talking to the primary memory, which is RAM, and that's where the program is stored in RAM. The program counter, which is pointing to the first instruction in that program. So it'll be like, oh, what's the next instruction I'm going to execute? And it's an address in memory. So like it could be like, let's just say it's 0, the first address. So it's pointing to 000, whatever, you know. And then what will happen is it fetches the instruction from that. It then decodes it, which is a decoding bit, to see what it's got to do. Then it executes it, and that could be to add something, move something from one place to another. And then afterwards, the program counter is incremented. So it goes up by 1. So it points to the next instruction. And this cycle repeats and repeats. There is a little bit more to this, but the video link will explain it in a greater detail. It's quite, you need a bit of a visual with this, and it's got a really good video of it where someone demonstrates it. So I'll just briefly talk about the fetch, decode, execute. But if you're in the exam, try to remember main things like the program counter points to what instruction we're executing. And just remember that it fetches an instruction, it decodes the instruction, it executes the instruction, and the program counter is incremented. And then it repeats over and over again. Right, so we're just going to have a look at the common CPU components, so common parts of the central processing unit. So the arithmetic logic unit is the part of the CPU that performs calculations and logic operations. So in the lessons where we did the Boolean logic gates, if you've done them yet, where you look at and, or, and not gates, that's basically what's going on in the arithmetic logic unit. It really is actually the bit of the CPU that does all of the actual clever stuff. It's the bit that can do all the maths, do all the checking, do all the logic. That's the bit that does everything really. So that's the arithmetic logic unit. The control unit is a unit, don't forget, so that means it's got many things inside it, that form part of the central processing unit, so there's a unit inside a unit. And inside the control unit, one of the main things is the clock. So when you hear before, you'll hear about clock speed, and we've done that in class, the clock that pulses, tick, 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 to tell the computer to execute. And it does send out a signal. It says go, go, go. Billions of times a second. That is part of the control unit. So the clock is in there. And the control unit also sort of controls data flow between the parts. Like it's the parts that control like getting the stuff and, putting the stuff places. So cache. We're going to talk about cache much later because it's here. But all you've got to understand right at this second is that it's a very fast memory that stores recent data to be reused. But as I said, I'll go through that more here. A register, you might see this a lot. Now, when you see register, you've got like different registers and different things. A register is a really small but extremely fast bit of memory in the CPU. So, for example, we'll talk in a minute about the accumulator that stores like the current result of any math that's going on. That's a bit of memory and it's in the CPU, and that is a register. It doesn't have register in its name, but it is. The program counter that stores where the next instruction is in memory, that is a register, because a register is a piece of like RAM, but a very fast memory. inside the CPU. But it's tiny, tiny. It normally stores like, one memory address or one number or one, two or three things. You might see the term bus. A bus is just a circuit that connects components together. So how the CPU talks to the RAM is through a bus. The two main ones are the address bus and the data bus, but all you've got to understand is that the address bus sends addresses, data bus sends data, kind of self-explanatory, and they allow data to flow between things, basically. Think of them as like wires that go between stuff. That's essentially what they are. So you'll hear about this von Neumann architecture a lot. Essentially, he came up with the idea of storing both the program data and the program instructions in memory. So before, if you were, say, running Paint, although I didn't have Paint then, but let's just say you were, Paint would be not loaded into RAM. That would be running off your secondary storage, and only the image you were drawing would be stored in RAM. But von Neumann came up with the idea is, wouldn't it be a lot quicker if we loaded the program into RAM? Might be a bit of a delay at the start when you're loading it, but once you've loaded it, it's now in this very fast RAM. So actually the program itself is in RAM as well as the data. So that's what modern architecture uses, still used today. So when you load Paint, you click on it, double click on it. It waits for a few seconds while it moves it into RAM. And then the program counter points to the start of the program address in RAM. And then it executes the program from RAM. And then obviously any drawings you're doing and pictures you're touching up, they're in RAM as well. Right, so the memory address register, that holds the address of the current instructions to be fetched from memory. So remember, the program counter holds the next instruction to be fetched. So basically, when you're getting instructions from memory, the memory address register stores where the address that you want to get it from, and then you get it from the memory data register. Now you might think, why do you have a program counter and that? Well, this is part of the system that actually gets the memory. So it gets the data. So it needs to know, this circuit, basically part of it, needs to know where from memory am I getting the data from. The program counter stores the next instruction to be fetched from memory, but this is the system that actually gets it. So you put that into there, then it gets the data and it stores the actual data into the memory data register. I've been through the program counter that holds the memory address of the next instruction to be fetched from main memory. So it's the next instruction you're going to execute. And the accumulator, it holds the intermediate value in math or logical calculations. So for example, if we were doing 3 plus 4 plus 5, it might store 3, then 7, and then 12. Because it's storing 3 at first, then you add 4 and it goes to 7, and you add 5 and it goes to 12. So think of it like that sort of screen on the calculator. Every time you press equals, it's storing the current value. Right, that's quite the tricky bit. That's the most difficult part of the course, I think, is 1.1. But anyway, so on to a more interesting and simpler topic. So the CPU performance. So there are 3 main characteristics of a CPU that you can use to decide how fast it might run. The clock speed, cache size, and number of cores. So the clock speed. Now what the clock speed is, every time that the computer performs an instruction, it does this when the clock ticks. Like that. Bang, bang, bang. And how fast it ticks is what the clock speed is. So basically, it essentially is how many instructions can be performed by the processor per second. It's measured in hertz, which basically means per second. So a 3 gigahertz processor could do 3 billion instructions per second. Just understand that in a CPU, though, you may have more than one processor. So as you've got cores. So that doesn't mean that the CPU can do 3 billion. It means that one of the cores can do 3 billion. So if you had 2 cores, you could, in theory, do 6 billion. So cache size. Right. Now this really confuses students. So cache stores the recently used data and instructions. It's a lot faster than RAM, right? So when normally the CPU gets data and instructions out of RAM. But often data and instructions are reused. It's apparently, I think it's 60% of the data that you use, you've asked for in the last few seconds or whatever. So basically, some uncommon idea is if we store, say a meg or 3 meg or 10 meg or whatever of the last data and instructions that we used, if we need to get it again, rather than getting it from RAM, we get it from cache. And so basically, that's what it does. So the larger the cache, the more likely the data we want is in there. So if you only have like, 1 meg of cache, then you've only got 1 meg's worth of data. So, if I've got 10 megs of cache, I've got 10 meg of the data that was used recently. So in theory, it's 10 times more likely to be in there. But I will go through that in some of the questions that I answer in the other video. So, number of cores. Inside a CPU, there is often more than one processing unit. The number of cores shows how many there are in the CPU. A quad core would mean there are 4 processing units are in the CPU. So basically, inside modern CPUs, there's more than one processing unit, more than one brain. So each of them will run at, they don't actually have to run at the exact same clock speed, but when you buy a processor, they are set sort of like 3.6, but in modern processors they can actually run each of them sort of differently, but they're still sort of designed to run at 3.6, and they might up and down clock them, but that's getting a bit too complicated. So just in essence, sort of think that they're all the same speed. Okay. But basically, so if you had a quad core 3 gigahertz processor, that means you've got 4 processors running at 3 gigahertz a time. All right. There we go. Now I'm going to quickly show you my example. Just run this little executable. You may have seen this lesson. All right, it should come up in a second. There we go. And this will demonstrate the 3 parts. So let's have a look at clock speed. Okay, so let's set this little man. Imagine this is the CPU executing an instruction. So I'm going to put an instruction out. It goes, fetches the instruction, and executes it. Bang. So as you can see, if I've got a slow or low clock speed, it just takes a long time to fetch and execute instruction. It can only do so many per second. Obviously, in this case, it can't even do 1 per second. But if I've got a faster clock speed, then it can do more per second. Okay, so that's not rocket science. That's just the speed. The faster it is, the more instructions executed per second. Okay, that's a single core. Let's go to quad core. Now I've got 4 of them. Now, you might think that's now 4 times faster because there's 4 of them. And in theory, that could be possible, but only if there's enough tasks. If I don't put enough tasks out, let's just click like this speed, get a nice speed up. You can see here that I've actually never, ever used the 4th core. And even when I do use a 3rd core, in fact, it's very rarely at the moment. Oh, there, I've got one. It's not actually 3 times faster than it was before. Or 4 times faster for 4. So the point is, unless there are enough tasks for the CPU to perform, then the extra cores will essentially be wasted. And so I'll go through that in a minute. So now, of course, I've got loads of tasks. And if I go back to 1 and put that many out, you can see that I'm obviously significantly faster with the 4. So you can see that as long as there are enough tasks to do, then having more cores is better. So this is quite common like in gaming, okay? I'll go back to that. So when you're playing a game, you tend to be running the game. That's all you're running. Oh, excuse me. So you're running that game, and obviously you're still running it in an operating system. So it's not only doing the game. In the background, the antivirus is still running and the other stuff. But basically, modern CPUs are like 8 core and above. So you might only be using 2 or 3 cores. The game will only probably run in 1 or 2 cores, maybe 3. So the point is that really for a game, you want a higher clock speed. I'm not saying that more cores aren't great, and obviously as you get a better processor, they tend to sort of go up. You don't tend to get a very slow clock speed, very high core, but it's why some of the bigger CPUs, like you might find a CPU, something like the Threadripper, and think, wow, that's a £2,000 CPU, that's great for gaming. But actually, it's not got a very high clock speed. What it has is a ridiculous number of cores, like 64 or 128 or 256. And so that's better for things like video editing, where the program can break down the task into little sections of the screen, or 3D design or things like that, because once again, they can break down the screen into like 256 chunks, and then each bit of the processor does one part of the screen, and that's quite common. So it's not always that the most expensive processor is great for gaming, for example. It's why a bit Intel is still sort of, although apparently in January it's going to change, doing very well in gaming. It's still slightly better than AMD because they have a higher clock speed than AMD. But this is obviously, might be out of date by the time you watch this, because AMD apparently in January 2021 are releasing some that are beating it, but we'll see. But the point is that higher clock speed is better for when there's less tasks, and more cores are better when there's more tasks. But don't get me wrong, obviously high clock speed and more cores is the best overall. Right, so let's have a look at cache. So cache, there's my wonderful drawing of RAM, look at that. So let's imagine you've got no cache, okay? And I put a task out. Now this is more like what would really happen. It goes and sees the blue task and it has to go and get it from the blue memory. It goes and sees a grey task, it needs the data for the grey, so it goes and gets it from the grey memory. And this is essentially what would happen. This is more like real. You have to go and see the task and then get the data. So it sees the memory address, it's decoding it and saying, right, I need to get the data from whatever address that is, and goes and gets it. Now, there's no cache at the moment. Now, if I have cache, let's reset it. If I have 2 blocks of cache, so this can only store two bits of information. Obviously, that's not real. It'd be like millions. So let's do a few tasks. So you can see that it's done a green task and it's storing green in there. It's done a grey task and it's got to go all the way back to RAM to get grey. So now I've got green and grey. Now, when I get to this grey task, we've been quite lucky here. It will go straight back because it doesn't need to go back to RAM because it already has that. Oh, it's got a blue task and it's going to go and get. And as you can see in cache, the stuff will get pushed out. Now, it's not quite as simple as that because the operating system will do some clever looking at it to see what cache should say. But basically, think of it as it stores recently used stuff. So if I click there, look, it's grey, it can go there. It no longer has to go to RAM. It can use the very quick cache. Now, a common question in the exam is to say, why does increasing the cache size make it faster? And students don't answer that question. They answer, what does cache do? And that's okay. You want to say what cache does, but then you want to say, having more cache means it's more likely, because now I've got blue, yeah, blue's in there. Okay, so now I'm going to have 3/4 of the instructions in there. So the only one I don't have is green. Well, there you go. So all 3 of these are getting done. So you can see that if I've got more cache, then it's more likely that I'm going to find the data I want in cache. It's not really rocket science. Right, so that is cores and cache and clock speed. Okay, last but not least in this, in a nutshell, 1.1, embedded systems. Oh, actually, I'll just do this bit quickly, sorry. So just in theory, higher clock speed is better when you're performing few tasks. Doubling the cores doesn't necessarily mean the CPU is twice as fast, as there needs to be work for both cores to do. Otherwise, one may be idle. I always do, like, let's say we're building a brick wall, but it's only 2 meters wide by 2 meters tall. If I had 100 builders on it, it's not going to be 100 times faster than one builder because they'd all get in each other's way. That there's not enough work for them to do. So just remember that the cores are only useful if they're being used, right? So an embedded system is a small computer that forms part of a larger system, device or machine. It includes both the hardware and software, sometimes called firmware. So examples, I'm not going to talk about this too much because it's so easy. An embedded system is just basically a small computer that's designed for a specific job. So think about like a central heating system that's got a little thermostat on it. You know, like inside, I know this is really boring, but inside a car engine, the actual engine's got little computers in it that open and close valves based on like oxygen level. Well, that's an embedded system. It's not putting an Intel bloody i9 in there. It's got a specifically designed little processor that's designed with the hardware in mind. You know, it's the hardware and software all combined in this little unit, and that whole job is to open and close things if the oxygen level is too high or whatever. And the same as dishwashers. You know, a dishwasher is an embedded system. The opposite of an embedded system, by the way, is a general purpose system. So that's what you're thinking about when you use a PC. And the main difference is that an embedded system, its job is one and done. You're not supposed to reprogram it. You make the embedded system is not supposed to be changed by the user and reprogrammed to do something else. You can't make a little app and stick it on there like a little program. It is designed and created to do one or few tasks, and it does those tasks, right? So why would they use an embedded system over a general purpose system? Because surely if it's general purpose, it can do more. Well, cost. So basically, because they're limited in function, it means they're cheaper to design and build. Okay, if there's a little tiny processor inside the engine and all it's got to do is open and close a valve, you don't want a £400 CPU and cooler running it. They also require less power because if they're not requiring so much speed, because they probably don't need to be that fast, then they don't need as much power. And power is very important in embedded systems. When you buy a dishwasher, you're going to run it how many times a day. You don't want it to take up more than your PC does. Yeah, so basically, essentially it's cheaper because they need less powerful processing, they're cheaper to build. So less power to run, cheaper to design, and less expensive processors. That's basically it. So after this, have a look at my video where I'll go through some questions on this unit, and then good luck on the next one.